This is Senior Project Group J, FPGA-based logic analyzer demo and final design review. As an introduction, a logic analyzer is an electronic instrument used to capture, display, and usually decode multiple signals from a digital system. Logic analyzers are incredibly useful for testing digital systems, and by using an FPGA and a PC GUI, you have a small instrument you can take with you anywhere. As far as roles and responsibilities, we have the project lead and digital design lead, Drew.
I'm the GUI and software lead, Josue. The objective was to design, build, and test an FPGA-based logic analyzer with a simple GUI for control, operation, and visualization. This consisted of three main groups: digital design, simulating and implementing of the FPGA prototype; software design and integrating of a GUI to control the prototype; testing and verifying the prototype with external systems.
Logic analyzers traditionally function like in the blue boxes. By using an FPGA, you gain the functionality necessary but with very small footprint, which should make it portable without a loss in functionality. The figure below shows the traditional system in blue and the project system in green. Looking at the traditional system, you have input probes, an external clock input, you have some kind of sampling system, you have some kind of clock management system, you have some kind of triggering system, and then you have your memory group and your analysis and display.
The FPGA serves as the logic analyzer. The power and serial connection is used to send the data over to the computer, which then uses the GUI to represent the information that will be discussed in the later slides. The LEDs serve as a way to indicate the logic analyzer is performing certain functions. Then the probes are being used to trigger channels.
The abbreviated requirements are: shall be able to simultaneously sample on at least 8 channels, shall be able to sample at a rate of at least 100 megasamples per second, shall be able to trigger from any of the channels, shall be able to decode common protocols, and shall be able to be controlled from an external GUI. The budget is very significantly skewed towards the FPGA, so we just wanted to make a note that you could get away with a much cheaper FPGA here. We go over utilization a bit later, but you could probably get by with one more on the range of $10 to $30.
The control page has 12 buttons with different functions. The connect button does exactly what it sounds like. It connects the GUI to the logic analyzer. The start button starts taking the data from the logic analyzer. The reset button resets all previous configurations to default values. The send configuration button sends the configurations based on what's on the config window. The disconnect button disconnects or closes whatever process is going on. The update config button updates the parameter based on what's in the config window. Export CSV exports the data into the working directory. Import CSV imports a CSV file which is later used in the decode window. Export post view exports the gathered data. Both the PWM buttons are used to start the PWM based on the configuration in the config window or to clear it. The image is also a button and it plots the data in the user's default internet browser. The config window has a trigger mode with different types of triggering modes. The trigger channel selects a channel on the logic analyzer, then the frequency and timeout can be typed in the text box. The COM port is selected by typing the location, for example COM7, and the PWM duty cycle can be set from 0 to 1. All these configurations are then later used in the update config button in the main control window. The decode window is used to decode the data imported from the CSV file. It can decode I2C, SPI, UART, by setting the right channels, and if decoding UART, you can set the baud rate. The decoded results will be shown in the terminal window. If this continued later on, it would be a good idea to have a text box on the decode window and have it display the values on there instead of the terminal, especially if making a .exe. This is the test setup for the SPI, and the I2C setup was tested the same way, just not shown here. The microcontroller software was written in C++ using the embed software and then uploaded to the board.
This is Senior Project Group FPGA-based logic analyzer. So first, to show off the demo, we're going to just launch the GUI. You can see the GUI now here, so I'm going to hide the command window. Now that the GUI is launched, we can come over to the config. We can change some modes so that you'll be able to see some LEDs change on the board. So we'll change it to trigger on the sampling clock, channel 7, and we'll put the PWM duty cycle to 0.5. Then we'll come back to the control tab. We'll connect to the logic analyzer. We'll update the configuration settings. We'll send the configuration settings. You'll now see some of the LEDs on the board have been changed. We can reset those changes to go back to the default values to see some other ones. We can send the PWM. If you measure with the multimeter, you'll see it measures about 1.6 something volts because half of 3.3. If we go back to the config page, we can change the PWM to 0.1. Come back to the control page and send the PWM. You'll now see the LED is much dimmer. We can clear the PWM, and then we can go back to the config, go back to our default settings. This is trigger on any change. So then we can hit start, and we can plot the data. So as you can see here, we can zoom in on the plots. So if we keep zooming in, we can see the SPI signal here. This is our S clock channel. This is our CS channel. This is our MOSI channel. This is our MISO channel. Now that we've seen that plot, we can go back to the GUI, and the command window. I'm going to keep the command window down here. So if we go over to the decode page, we know this is an SPI signal, so we know that, let's see, S clock was channel 3, CS was channel 0, then we have MOSI was channel 1, MISO is channel 2, and that's pretty easy to see if we just look here, S clock, MOSI, CS, and MISO. We're just matching those up so that we can decode them. Okay. Now we can just hit the decode SPI, and you can see it decoded those packets. So we see it sending FA, F7, FD, which is just saying I want the temperature, I want the pressure, and I want the humidity. And this is just the reply the temperature, pressure, and humidity sensor is sending back, which is neat. After that, what we can do is we can go through here, and we can actually export that as a CSV if we want. I'll go ahead and do that now, and it just exports into the working directory. Now, since we use logic analyzers for more than SPI, we can import a CSV, which if I hit that button, you can see the file explorer popped up. So I can navigate to some old captures I did. So here's an I2C capture, and then we can plot that capture. Go back to just Chrome being popped up. And if we zoom in on one of those, here we can see the I2C transaction. We can also decode that. So if we go to the decoding page, back into the GUI, so we know that SCL happened to be channel 0, STA happened to be channel 1. We can decode SPI. You can see that it is basically just reading the requesting to read address 76. It's acknowledging. This is saying I want to read the, down here is saying I want to read the temperature. This is reading it. This is the temperature that it read. It's saying it's done. That's working. If we want to look at another one, we can come back over here, import another CSV. This is a UART transmit. We'll have to change the mode that was done. Yep. config. And then if we plot that, we have the UART transmit data. So if we come back to the enter command window, go over to our decoding, so that was on channel 1 and channel 0. We have no RX, and the baud rate was 9600 bits per second. So if we decode UART, I'm scrolled up. Yep. You can see it decoded as that and that, so 304130 in hex. Another neat feature we have is that we can actually go back to the control page, hide the command window, and then we have this export pulse view button, which is just a button that allows us to use an open source software to visualize. Once that launches, I'm going to have to hide a bunch of windows. Okay, so this is the open source software, which comes with a bunch of decoders that we can also access. So in this case, I want the UART decoder. I know that the TX line happens to be channel 1. I know that it's not that. Data bits, parity, okay. And you can see we get the same 30, 41, 30, which is the same thing we got before. This is the results measuring an SPI signal. What was done was the frequency was continually increased, and it was attempted to decode and look for crosstalk on the plots. What happened was crosstalk only really occurred around 20 megahertz onwards, and that was caught by a software glitch filter. And then the decoding started to fail around 20 megahertz, but was still mostly successful. The assumption is the decoding started to fail as the Nyquist theorem was starting to be invalidated with the harmonics of the general clock square wave. This is the results measuring the simple PWM DAC. It was measured over a simple one-pole RC low-pass filter. It has 8 bits of resolution, so it has a voltage resolution of about 12.9 millivolts, and it's controllable by the GUI, so it could be used to test an analog to digital converter. This is the view from the logic analyzer side of things. You can see that with the 50% duty cycle, it's on and off 50% of the time, and with the 25% duty cycle, it's on and off 25% of the time.
There were a few issues with the design. Occasionally glitch pulses were seen when channels were floating or in use. This was simply solved by grounding the unused channels and using a software glitch filter on the channels in use to catch the glitch pulses. Secondly, there was a limit on how fast data could be extracted from the board. This was solved by using the simple on-change mode, as well as having an internal buffer on the FPGA to store samples before sending them over to the interface.
A few additional notes. The data bandwidth was limited by the only interface to talk to the PC present on the FPGA being a UART to serial converter chip, and it limited out at about 2 megabits per second, while the data to continuously stream would require about 800 megabits per second for sampling at 100 megahertz on the 8 channels. If you did have a board with USB 3.0 or gigabit Ethernet, you could theoretically continuously stream data off the board like Cell A does with their logic analyzers. And main control is done through the GUI, but since this is built all upon an object-oriented programming methodology in Python, it is easy to script controlling the logic analyzer through Jupyter Notebooks. Finally, the worst negative slack was 2.48 nanoseconds, which means the maximum frequency or sample rate the system could currently run at is 133 megahertz. This could likely be driven higher by routing more aggressively or investigating worse paths for solutions. Here's the utilization comparison between the project's logic analyzer and Xilinx internal logic analyzer IP. You can notice the Xilinx ILA uses about 1500 more lookup tables and 3700 more flip-flops. It uses the same amount of RAM if you factor in that it is using VRAM to take away from some of the lookup table RAM. Finally, we wanted to look at some possible future additions for future senior project goers. They could integrate an external analog to digital converter or an on-chip analog to digital converter to act as an oscilloscope for the device. They could integrate a more complex digital to analog converter for use as an arbitrary waveform generator. Finally, they could output some common digital protocols with the FPGA itself to test external electronics without a proxy device to send out pulses to test. Any questions?